So talking about singular value decomposition or SVD, it's one of the most important tools in linear algebra and data science. At a high level, SVD is a data reduction tool. So imagine you have a huge data set or a megapixel image or a high resolution video. SVD takes all of the high dimensional information and distill it into most important features. So you might be thinking, why does this matter? Because once you reduce your data to this essential feature, you can compress image, video, solve large system of equation and regression model, understand dominant pattern in data through PCA, which is also known as principal component analysis, and even power application like Google PageRank, facial recognition, and Netflix recommendation. So that's the higher level story. SVD takes something large, complex, and break it down into smaller, meaningful pieces. Now let's move from the bigger picture to the mathematics of SVD. Here is a formal definition where A equals to U d V transpose. So here in place of D we can also use sigma, and for every matrix A, no matter its shape, can be decomposed into three pieces. U is a unitary matrix. Its columns are orthogonal left singular vector. And similarly, V is also a unitary. Its columns are right singular vector. And in place of D, which is sigma, is a diagonal matrix of a singular value, which are non-negative number usually arranged from largest to the smallest. Intuitively, U and V provide orthonormal base for the space, while sigma tells us how much to stretch or shrink along each direction. You can think of it as A equals to U dot sigma dot V transpose, where U rotates, E scales, and V rotates again. Another way to see it is by looking at the column vector. Another way to see it is by looking at the data matrix. Suppose we have A equals to A1, A2 to up to AN, a collection of column vector. For example, snapshot or images. SVD decompose A into orthogonal component, where A equals to U dot sigma dot V transpose. This means the structure of the data is captured by U and V, while the importance of each component is captured by the singular value in sigma. So mathematically, SVD is giving us a rotation plus scaling plus rotation structure, and at the same time telling us which direction is our data are the most importance. Now let's actually compute an SVD by hand. We will use the small 22 matrix, which will look like this. This will let us see how the decomposition works step by step. First step is to form A transpose A. Multiplying this gives us a new matrix with a new value. This is a symmetric, which is exactly what we want, because symmetric matrix have real eigenvalue and orthogonal vectors. The next, we compute the eigenvalue of A transpose A. The characteristic polynomial is 10 minus A whole square minus 36. Solving this equation gives us an eigenvalue of 16 and 4. Singular value of A are just the square root of these eigenvalues 16 and 4. So we get sigma 1 and sigma 2 is 4 and 0. We will then put this value into the diagonal matrix sigma. So now the eigenvector of A transpose A give us the column of V. For eigenvalue of 16, we get V1 is this value and V2 is this. So the orthogonal matrix V look like this. To get U, we use the formula like this and plug in the value we get from the above, which will result in giving the value of U1 and U2 same is V1 and V2. So interestingly, U equals to V for these particular matrices. So finally we have decomposed A into, using our SVD formula, A dot sigma dot V transpose, using the value we have gained above. So this shows how SVD takes our matrix and factor it into two orthogonal matrices and a diagonal scaling matrix. Now that we have walked through an example by hand, let's see how we can compute the SVD in Python. We will use NumPy, which has a built-in function linearalgebra.svd that does all the heavy lifting. Here is our same matrix from the previous example. We will run np.linearalgebra.svd, which will return in three output: U, the matrix of left singular vector, S, a vector of singular value, and V transpose, the transpose of a right singular vector. And if you compute this result with our hand calculation, they match exactly, just up to tiny float point difference. Notice that NumPy gives us V1 and V transpose is orthogonal matrix and singular value 4, 0. This perfectly match our manual decomposition, so the theory and computational agrees. But the real power of SVD is in application. One famous use is phase comprehension. Here is the idea. We treat an image as a big matrix of pixel value. Using SVD, we can approximate that image use only the top k singular value, capturing most of the information with less storage. In this code, I load an image, compute it SVD, and then construct it using only the top k singular value. I will show you what happened for k 5, 20, and 100. With just 5 singular value, the image is blurry but recognizable. With 20, it becomes much clearer. With 100, it nearly indistinguishable from the original. The takeaway is that most of the important information in the image is captured by the largest singular value, while the smaller one contribute only fine detail or noise. To recap, every matrix can be decomposed into U, sigma, V transpose, where U and V give orthogonal direction while sigma shows how important each direction is. By keeping only the top singular values, we can simplify, compress, and understand data more efficiently. That's why SVD is both a beautiful piece of linear algebra and a cornerstone in modern data science.